Good morning, everyone. So I'm gonna continue with my videos. I'm still working in the second part for the molecular dynamics tutorial, but it's gonna take a little bit of time because I'm working on how to explain to the students because my idea was to make something that even high school students can understand. So it's really a bit hard uh, because I want to go into the ensembles that we have, like the NPT or the NVE, etc. So it's gonna take a while for me to try to do a decent presentation for that. But anyways, I still have some free time because we had to work at home, so it's more like a hobby for me. I have no idea if I'm gonna continue with these videos because once everything comes back to normal, more likely I'm not gonna have more time to do this. But regardless, if people give me comments, feedback, and they like my videos, probably I can continue doing this and but anyways, I'm gonna give you an introduction and I'm gonna read the title, the Bravais Lattice. So I'm gonna give you an introduction of how to make crystals. Because when you, this is related to the molecular dynamics video, because when you are trying to run simulations, you had to remember that you had to input the information into the computer. Okay, and the problem that we have as people who are working in computer simulation is that you have to grab the experiments data you have and put that into an input file. Okay, so I'm gonna go quickly into this presentation. I don't want to make it last more than 20 minutes. So we're gonna go and see the crystal probably have properties of translation and rotation, okay? And there are sequences, okay? They are found everywhere in nature. And then we're gonna go into how to define a crystal, okay? And that's gonna be, I'm gonna put an easy way to define what is a crystal, okay? Based on the Bravais Lattice. So we can see the sequences are everywhere. You can see drawings, probably where you have the DNA. You have a sunflower right here, probably you have numbers. You have to have something that it's have a way to arrange, okay? And there are rules on how they bond together. And also they have something that's called their periodic. Okay, so if you translate certain number of units, you're gonna see that you repeat the same image. If you continue another space of units, you're gonna see the same sequence. So pretty much has we define a crystal. If we go into the atoms, okay, we have to remember the way that we visualize the atoms is pretty much using bolt sticks. You remember from middle school or high school, you're gonna see that you have this kind of kits. And the students pretty much they bond together the bonds and the big compounds and they make molecules. Okay. In nature we have crystals. Okay. Examples of crystals that we have in nature, for example, the table salt. That's usually something that you're gonna find at home. Okay, for cooking. Then you have other materials like gold. Okay, that's an FCC structure. And typically when you see these structures in nature, the crystal is gonna be polycrystalline because crystals grow in different directions, okay? And there are boundaries, and because when you are in nature, okay, there are many conditions that you have to control, like the temperature and the pressure, the amount of concentration, and etc. Only when you're in lab conditions, you can try and make perfect crystals, but even in laboratories, it's a little bit hard to control all the variables that you have around. So you have the crystalline, the polycrystalline, and amorphous. Now if we go into the next image, because some people have misconception of what is a crystal, molecules are not a crystal. Okay, some people have told me that they are not crystal. They don't have all the translation and rotation symmetries of a crystal, so they are not defined as that. And nanotubes, nanoparticles, they are not crystals. Okay, they are quasi-crystals, and actually if you go, I don't remember the year it was, I think it was one of the Nobel Prizes on chemistry. They do a really nice introduction to quasi-crystals, okay, and many nanoparticles go into that category, but they are not crystal. They don't have all these properties. Another one, glass. Okay, glass is not a crystal. Okay, some people may try to look at this image and say this is crystal, but no, this is more like an amorphous thing. It's not a solid, it's not a liquid, it's something in between. Okay, so now you're gonna ask me, well, what is a crystal? Well, I'm not gonna read everything. I'm gonna go here and say a crystal is made of periodic arrangement. Okay, I want to define that is something that have periodic arrangement of one or more atoms. Okay, how are you gonna go and map all the atoms? That's the reason we have this R vector right here. That's R equal N1 A1 plus N2 A2 plus N3 A3, when Ni are the integers and Ai are the primitive vectors. We have to understand that this is going to map all the lattice points. I'm going to tell you why in the next slide. When we define a crystal, okay, we have to go into the Bravais Lattice. So we have 14 ways that we can make crystals. Okay, so everything that have these shapes is considered a crystal. Okay, now the tricky part is that the atoms can go inside of the lattices. So they can go, let's call it the boxes. They can go, for example, it has simply cubic. Atoms can go inside of a simply cubic. Okay, so they are, even if we have 14 lattices, we can have not an infinite number but a large number of crystals. Okay, because the way that you can put the atoms inside the structure, it can be in different ways. Okay, now of these 14, only 7 are considered crystal systems, because if you see the simple cubic right here, you can have the body center cubic or the face center cubic if you had a simple cubic, because you only have to put atoms inside a structure. Okay, the same happen with a simple tetragonal, or the same happen with orthorhombic. If you had a simply orthorhombic, you already had a body center, and you already had the face center, and you already have the face center orthorhombic. Okay, so in reality you have, let's count it, 1, 2, 3, 4, 5, 6, 7. You actually have 7 crystal systems. I'm gonna name them one by one: simply cubic, tetragonal, orthorhombic, monoclinic, rhombohedral, hexagonal, and triclinic. So we have 7 crystal systems, but in reality we have 14 Bravais lattices, and we have 2 Tory space groups. And I'm going to go into the space groups in this presentation, because that's not the idea that I want to give in this presentation, but there is a relation between the crystal system and the space group. So if you have a space group, you can go back to the crystal system. Okay, and if you have a crystal system, you can go back to the space group. So there's a connection. And there really has to be a connection between this kind of crystal systems and groups. So I'm going to give an example of how to make a crystal structure. Okay, remember, like I told you before, we had to have crystal system, and then the atoms are gonna go inside. Okay. If I know how the atoms goes inside the box, then I can make the crystal. So here we have an easy example because it's actually a simply cubic structure. We can see that by the primitive vector that we have right here, and the compound that we have is calcium, titanium, and oxygen. We have 3 oxygens, okay, and we have the basis vectors. The basis vectors tell you where are gonna be the atoms, okay. Having that, I can make my crystal structure. So I can go here. I'm gonna show you the emitter program for running or for making crystals, and I'm gonna try to make these structures right here. So I'm gonna go into option number 7, that is make a new lattice structure. So I'm gonna press option number 7, and then it asks me it's gonna be simply cubic, face center cubic, or custom. This program is only working for cubic structures and also for tetragonal, okay, and orthorhombic. But because you know the simply cubic and the tetragonal are very similar, the only difference is in the length, okay, the length of the box, okay. In a simple cubic, you already know that the length, all the lengths are gonna be the same, but you can see here in the tetragonal, A is equal to B, but B is not equal to C, so you don't have the same length of all the boxes, but the angles are inside, they always make 90 degrees like you have in a simple cubic. So I think that this program is also going to work for the tetragonal orthorhombic. But if we want to try something like a monoclinic or the other ones that we have below right here, then we have to extend, okay, this software. But regardless of that, that's the reason why I put a simple cubic structure, because it's something easy to do. So it's gonna be simply cubic, okay. But then it's gonna ask me for a lattice constant. Here I'm gonna put 3.304, okay, because I have no idea, and actually they had to look at the information from experimental data, okay. So I put the number, and I like the 3.304, okay, but it's not the exact lattice constant number. Then it's gonna ask me for the size of the computational box. So I want to make it only to be one sample, so I had to put 1, 1, 1. Then how many atoms you have in the box? So we have 5 atoms, so we have 5. I said 4 or 5. No, I have 5. I have 5 basis vectors. So the first one, I'm gonna put that we have 5. The first one is a 0, 0, 0. Okay. That one is gonna be calcium. I'm gonna put atomic mass equals to 1 for calcium. Right now it doesn't matter because we are looking at the structure, but if you run simulation and molecular dynamics or ab initio, etc., you have to put the correct atomic mass. Then let's go into another element. It's gonna be titanium. It's gonna be 0.5, 0.5, 0.5. And then I'm gonna put the element name is Ti. Atomic mass, I'm gonna put 1. And let's go into the next one, oxygen. It's at 0, 0.5, 0.5. And atomic mass 1. Let's go into another one, 0.5, 0.5. Then I can put oxygen again, it's gonna be 1. And the last one is exactly the same. Okay, I have this, I can look at my structure pressing number 6. So I have calcium, titanium, oxygen. So I have a lattice that have 15 atoms. Okay, when I put that 000, it means that calcium it's on the corners. Okay, then I enter this right here, and then I'm gonna have this as an input file. So I'm gonna press option number 9 right here, and I can write. I can input that in different formats. I only want to put the XYZ coordinates. If I will run labs for molecular dynamics, I will put option C, but here I'm gonna select option A, and then I'm gonna put the name of my file, and we're done. So I can exit the program, and I can look at my file that I got. I have atoms right here, and actually I can go and visualize this on the computer. I can go and open this. There we go. This is my structure. Okay, so we can see that we have the calcium on the corners. We have the oxygen and the titanium. We have in the middle. Okay, so this is the structure that I made. And what I want to give people the idea. Oh, don't look at my Facebook because I go into what I want to give the idea is when we have the lattice structure and we know where all the atoms inside, we can make the structure. Okay, and so we had to have the lattice vectors. Probably it's gonna tell me what kind of lattice I have. Then I may go and input this information. This is where the atoms are inside. So if I have that, I can make any structure. Okay. Let's go into another one. I'm gonna go into sodium chloride. Okay. Well, we know that sodium chloride is a FCC structure. Run my program again. I'm gonna go and make a new lattice structure. I'm gonna put simply cubic, and then I'm gonna put the lattice constant is 5.6. And then I'm gonna make it now we're gonna make it 2 units. So I want to make it to be 2, 2, and I'm gonna put 0. Okay. But I only want to extend this. I only want you're gonna see what's gonna happen when I run this. So I have 2 atoms. The first one is 0, 0. It's gonna be chlorine. I'm gonna put atomic mass of 1. Then I go into sodium. That's gonna be 0.5, 0.5, 0.5. And I wanna put atomic mass of 1. I can see my lattice right here. Oh, it's a problem because I never got atoms here for. Oh, that's a problem I have right here. And then you're gonna run into this kind of problems when you're running the simulation. Probably that happened because I put that in the R quad was 0, so I'm gonna have to and I have to erase everything. So I'm gonna erase this. I'm gonna erase this because I don't want to make a mistake. So I'm gonna erase this. Then I'm gonna try again. Simply cubic. I'm gonna put 5.6. And then I'm gonna go into and I put 2, 2, 2. I have 2 atoms. 0, 0, chlorine. 1. The sodium isn't there. Okay. And then I can see that's gonna run fine. And I'm gonna write this on the computer. I'm gonna put here. I'm gonna put sodium chloride XYZ. Then I'm gonna exit. Then I'm gonna run this. And where's my sodium chloride? Right here. There we go. This is where I went to. Here we go. This is a sodium chloride. Okay. I have 2 to 2, so I have 2 in X, 2 in Y, and 2 in Z. Okay, that's the reason, because I put 0 and C. Actually had to put, if I want to make like 2, it will be like 2, 2, 1. Anyways, okay, here we go. It's an structure. You can see, if I can see the labels right here. Let's measure the distance between the chlorine, just to give an idea what we do. It's 5.6. Okay, so we're okay in that calculation. I'm gonna continue with another examples later on, but also something I want to really important when you run simulation is you want to check for overlapping of atoms, because sometimes when you are doing this calculation on the computer, if the atoms are too close together or they are overlapping, when you go and you run molecular dynamics, you're gonna have a lot of errors. So it's always good to check for overlapping atoms that you have for actually saving the input file into the computer. If I continue, they're gonna ask me where are the atoms. Well, typically when you are doing the crystal structures, you have to obtain the information for experiments. And how we know where are the atoms? Well, you have to use X-rays. Okay, so the people who do experiments, they're gonna have a diffraction pattern, the one that we have right here, and from this information we can make the lattice structure. It can be also for proteins, I mean molecules, compounds, etc. And while we have that information, we can make the input file to run that into the computer. Okay, but typically we want the lattice constant to be fine or to be obtained for experiments. Okay, sometimes using molecular dynamics or using ab initio calculation, we can obtain like the lattice constant by predicting the minimum and the energy and so on, but I'm not gonna go into that topic. But always you need experiments to confirm your results using a computer, regardless if you do it by ab initio or if you do another methods. Okay, so computer simulation, I'm not gonna read this because when you need to do computer simulation, you have to have the structure. And the way that we do a structure, just give me the Bravais Lattice, give me where are the atoms inside, and then I can make the structure. Okay, I'm gonna go now into nanoparticles. I'm gonna make a nanoparticle for you guys. I'm gonna go into option number 5 because I want to make a nanoparticle. Usually nanoparticles are platonic objects. So I'm gonna make a icosahedron D. So I'm gonna put here option number D. I'm gonna put the lattice. I'm gonna put 3.605, and I'm gonna put I want to be called atomic mass. I'm gonna put 1, and I'm gonna put a system size of 5. Okay, so I have my structure. I can look it at number 7. No, number 6. I'm sorry. You can see a number of atoms. Always you have to check for the overlapping. So I will put option number 12 just to make sure that we don't have any overlapping atoms, because we can have that kind of error. Then I'm gonna make it a little more fun. I'm gonna add defects to the structure. So if I go here and I can look at my option number 13, I can add defects. I'm gonna wait till for number 13. I'm gonna grab my my nanoparticle right here that have an ID of 0, and I'm gonna replace the atoms that we have in the structure by another element. So I'm gonna choose option B, and then I want 50% to be another element. So I'm gonna put, I want it to be silver, and then I want it to be mass of 1, and then I'm gonna replace my nanoparticle, press enter. You can see that now I have the gold and the silver together. Okay, so now I'm gonna save this. I'm gonna write as XYZ. I'm gonna put nanoparticle XYZ. I'm gonna exit. Okay, now I'm gonna see. I want to look at my structure. Where I put it, nanoparticles. There we go. This is my structure. This is a nanoparticle, and I don't know if we can go and let me see if I can zoom this because I don't see it. Oh my goodness, how is this? Let me cross it. There we go. Now you can see. It's a nanoparticle. It is a icosahedron. Okay, we have half of the elements are gold and half of the elements are silver. I just made this for fun right now, and we don't have any overlapping arms. Okay, I'm gonna exit right now. Now another option that we may have when you are trying to input, when you're trying to create a lattice is, for example, you want probably to rotate the computational box. You want to rotate your crystal structure. Probably you want to erase atoms. Okay. Probably you want to have like a cut plane. Okay. So let's say, oh, I want to have a cubic structure when I want to cut it in the 101 direction using the Miller indexes, so I can use a plane to cut. And there are options, but this is pretty much the basic that you need to have when you're making a crystal structure. And to summarize what I have right here, it's if you want to have an input file for making a lattice, give me this information and give me where the atom's gonna be inside, and then I can make the structure. Finally, here what we care about symmetry. I'm not gonna go into this because I was trying, but I'm running out of time. If you have symmetry, it will reduce the amount of calculation that you have to do. So it's really important to consider that. And you have symmetries that they can show up in the continuum. For example, it can show in the dielectric constant, it can show up in the elastic constant. You can see that when you have certain materials to the high specific symmetry, the number of elastic constant or the number of dielectric constants is going to reduce. Okay, so when you're trying to do calculations, it's going to be more easy to do than if you consider no symmetry. Okay, so anyways, this is my presentation. Please